Okay, thank you. It's an honor to be talking at this symposium, memorial symposium for Nambu. Sadly, I think I never had a conversation with Nambu, though I almost feel as if I had, because I visited Chicago many, many times, especially in the years when he was around, and I'd pass him in the hall and he would always smile at me. So I had a little piece of that. And of course, I've been influenced by his contributions to physics, which have sort of creeped into every corner of what we do now. And what I'll be talking about today will be black hole information. Okay, so over the last 3 years, a relationship, a triangular relationship, has emerged between 3 different topics, each of which has been studied for about half a century. And what are these 3 topics? Well, one of them are the so-called soft theorems in quantum field theories, which in their modern form date back to Weinberg in 1965, but really they were known in an only slightly different language by Francis Lowe or even Bloch and Nordsick decades earlier. And what these soft theorems say is that if you have a scattering amplitude in quantum field theory, in which one of the external particles is massless, and of particular interest is the case when it's a gauge particle or a graviton, that the low energy limit, if you take the energy of that external particle to 0, you get back the same amplitude without the particle times some function or operator A acting on the reduced amplitude. And these have been extremely important in making sense of quantum field theory and in calculations that are done daily for LHC scattering amplitudes and so on. Another subject which has had a lot of development, we could take this back to Arnowit, Dessner, and Misner, or Bondi, Vanderburg, Mesner, and Sachs, and in many different fields of physics, is the idea of asymptotic symmetries, and that those words mean many different things to many different people, but let me just lump it together as the studies of symmetries which naturally act on scattering states in the far past and future. Then the third, less well-known, but nevertheless somewhat developed topic is the phenomena of memory, which has mostly been studied in its gravitational form, but it has many other forms. That was discovered in 1974 by Zeldovich and Polnarov. It's a phenomena in which you disturb a system. The gravitational version of it is you, say, have a pair of inertial detectors, you disturb them in some way or another, and at LIGO, as we all know, they'll oscillate back and forth, but there's a DC part of that after that oscillation is done, they may not revert to their original positions, and that DC part has a lot of really interesting physics hidden in it, and there have been discussions over the years about measuring it, and indeed now with the likely increase in funding for gravitational wave physics and the hopeful launching of ELISA, which will be an ideal laboratory for measuring gravitational memory, we may hope that it is observed. Now, this triangle echoes throughout. There are many different versions of this triangle, so these 3 things are equivalent. I forgot to mention, roughly speaking, the soft theorems are Fourier transforms of the memory effect, Fourier transforms in time. The symmetries, the soft theorems are ward identities of the symmetries, and the memory effect can be thought of as being a result of transition between inequivalent vacua that are related by the asymptotic symmetries. And there are many different soft theorems. This applies to any kind of quantum theory or quantum gravitational theory, and there are many instances of this, and I'm not going to try to review all of them here. I'm going to kind of point it toward some work of the last couple months that relates it to, surprisingly, the black hole information problem. So what I'm going to do, the outline of this talk, is I'm going to describe some basic features of this triangle, and with it is associated, with the symmetries is associated an infinite number of conservation laws in all theories with gravity or electromagnetism. It will seem to be unrelated to what I'm going to be doing next, which is to review the black hole information paradox, but I'll then explain why it's relevant, and then I will describe some very recent work trying to get more into the guts of how this affects, these observations affect the physical process of black hole formation and evaporation and information flow. Okay, so I'm going to start with something extremely simple. Everybody knows that if we have an electric charge in flat space, that we get a radial electric field coming out of it that goes like E over 4 pi r squared. If you then boost that, you find that the radial component of the electric field is given by this somewhat complicated looking expression, and the length of the electric field vector, the radial electric field, is expanded in one direction and contracted in another. Now, I suspect Maxwell knew this 150 years ago, but I only understood it myself in the last 2 years. This expression has the rather, to me, surprising property that it is not single-valued as you go to infinite radius. It depends in a spatial direction. It depends on how you approach spatial infinity. And understanding this carefully is going to be the crux of everything I'm about to say. So let me draw a picture here. So here I've drawn the Penrose diagram for a single charge moving at constant velocity in Minkowski space. So in this diagram, light rays are going at 45 degrees. This is all of Minkowski space. This line here and this line here are what's called future null infinity. That's the place where light rays go to, and it's parametrized by retarded time. U is ordinary time minus radius. So if you keep U fixed, and if you're a light ray, you keep U fixed, you take R to infinity, you end up somewhere out here at future null infinity. Similarly, this is past null infinity, V equals T plus R. And a massive charged particle, even if you boost it, can't get out here. It has to start from past time like infinity and end at future time like infinity. In this picture, R, which are these lines, is getting smaller until the origin, and then it's going out to infinity. Now, if you rewrite the expression on the previous slide in terms of R and U, and take R to infinity, you get this expression. On the other hand, if you write it in terms of R and V, and take R to infinity, you get this leading order term, where X is just the Cartesian three-dimensional X. And these things differ by a sign. They're not equal. So if I start here, I compute the radioelectric field and it'll be constant along here. I go back down to here. I don't get the same thing as what I get up here. Very simple fact about the Lienard-Wiechert potential for electromagnetism. Now, this expression, it's not equal to itself at fixed angle, but notice that if I take x to minus x, this expression, spatial x to minus x, this expression turns into this one, so that the radial electric field up here, I'm going to call this the past of the future. The radial electric field at the past of the future is not the same as the radial electric field at the future of the past. They're not the same point. Physics is discontinuous there. Even Maxwell electromagnetism is discontinuous there. And in fact, it's not hard to show that this is true just by linear superposition for any number of inertial moving charges. And it's also not hard to show that if you take any number of interacting, scattering charges of arbitrary signs and solve for them in the usual way that Jackson taught us to do, you will find that this condition is obeyed on the leading term at large R of the radial component of the electric field. That is, in general, on the sphere at infinity, the radial component of the electric field at the past of the future is equal to its value at the antipodal point of the future of the past. Moreover, this boundary condition on the electromagnetic field is, in fact, as we'll see later, implicit in the Feynman rules for QED or any abelian gauge theory. Now, if these things are equal point-wise, so just to make things simple here, I'm going to introduce a function eventually I'm going to extend it over all of null infinity, and I could extend it over all of Minkowski space, which has the property that epsilon, that its value at the past of the future is the same as at any point on the sphere at the past of the future. It's the same as at the antipodal point of the future of the past. So that's what this function obeys. So if these things are equal pointwise, if FRU and FRV are equal pointwise, I can integrate them against any function of this form, and these integrals will be equal. So let me now define an infinite number of charges, and which, if I took epsilon to be a constant, this would just be the ordinary electric charge. But I now have two charges, one associated with the future, one associated with the past. They're exactly equal. So in any theory of electromagnetism, there are an infinite number of conserved charges, not just one. Now, for the special case where this thing is a constant, we could take this, that's the familiar case. We could take the charge at the past to the future. We could regard the past to the future as the boundary of future null infinity, and we could use Gauss's law and write it as an integral over all the outgoing charges. Similarly, over this green surface here. Similarly, we could take the future of the past and think of it as the boundary of past null infinity, and then we could use Gauss's law, write the charge as an integral over that surface. In fact, we could use Gauss's law and write it as the integral over any surface that ends there or there. And what we would learn is something we all knew, that in any scattering process, the sum of the ingoing charges is always equal to the sum of the outgoing charges. But this is just one, this very familiar statement, is just one of infinitely many statements which are all on equal footing. So what are these infinitely many other conservation laws? Well, now if we take a general function, we can still take this, this surface integral here and write as an integral over past null infinity. But now, the Gauss's law will give us a term which is a sum over the incoming charges, but weighted by an arbitrary function which depends on the angle from which they came in. By the way, for simplicity in this talk, I'm just going to consider massless charged particles which come in from null infinity. There is a similar, the whole story goes through actually in a very beautiful way. If you consider massive charged particles, which can only come in from past time like infinity, but it's substantially more elaborate. So I'm just going to consider this simple case, which captures the essence of what's going on. So now, obviously, if we take the incoming charges, weight them in an arbitrary way by their incoming angle, that's not going to equal the outgoing charges weighted in an arbitrary way by the angle. We need a correction term. But we can simply compute that correction term by just integrating by parts, and here's what we get. So this correction term, it's an integral over the whole past, and since when we integrate by parts, we get a term involving the derivative of epsilon. Now, I'm going to choose, we would get a true relation no matter how we choose it, but for simplicity, let me discuss the case where epsilon is chosen so that even though it depends on angle, it's constant with respect to retarded time in the past or advanced time in the future. So then I get an extra term like this. This is a component of the electromagnetic field contracted with a vector, the gradient of epsilon, which is tangent to the sphere at infinity. That is, it's a transverse component of the electromagnetic field. If I were to have an e to the I omega v here, in other words, then I would be doing a Fourier transform with respect to advanced time, and this would be a radiative mode of the electromagnetic field. I'm not doing that, so it's a zero mode of the electromagnetic field, which is called a soft photon. And because of the way this is appearing, it's a soft photon whose polarization is the derivative of this arbitrary function, epsilon. Now, by the way, so the extra term that we need to correct by is, right now I'm still doing classical physics, but I'm going to call this a soft photon because I'm going to go quantum a little bit later, and it's a useful language. So by the way, if we were working in, if our boundary conditions or gauge conditions make the V component, which is natural to do, makes a V component of the electric field be zero, then this thing is just the V derivative of the vector potential, and this V integral can be done, and this strange duck here, the correcting term, is the difference in the gauge potential at the past of the past and the future of the past. And so now, if it's a finite energy condition, the electromagnetic field will vanish at both the past and the future of the past, but there will be a gauge transformation relating them. a non-trivial gauge transformation relating them. So in some sense, this extra term lives not on all of null infinity, past null infinity, but it can naturally be thought of as living at the boundary. It's a kind of boundary term, and ultimately it has a sort of holographic nature, and it's a boundary term for the same reason we have boundary terms in ADS CFT and other kinds of holographic theories. Okay, so this is an exact conservation law in the classical theory. What about the quantum theory? Well, in the quantum theory, what we say is we have some outgoing quantum state at future null infinity, which is related by an operator called the S matrix to the ingoing states. And if this charge is conserved, it must commute with the S matrix. Or since S matrix is e to the IHT, it commutes with the Hamiltonian. Now, Q plus epsilon and Q minus epsilon are equal, but I'm denoting that we write Q minus epsilon, the form of writing this operator that's natural for acting on in states, and Q plus epsilon is the form that's natural for acting on out states. So what we have here is an infinite number of relationships for any given pair of incoming state and outgoing state. We have an infinite number of relationships. That is, one for any function epsilon on the two-sphere. This is a lot of relationships. And what is this conservation law? Well, it's very bizarre. Now, this Q, recall, had two terms. It had the odd duck, which was the soft photon, and then it had the other term, which basically gave acting on out states or in states, just became numbers proportional to the charge weighted by the function epsilon. So what is this conservation law telling us? Well, it's relating an S matrix element, this original S matrix element, with an additional soft photon to some numbers times the old soft photon, times the old S matrix element. So, of course, it would be just too much if we had discovered something absolutely completely new about electrodynamics. We haven't discovered something absolutely completely new about electrodynamics, but we have found a powerful new way of describing old facts about electrodynamics. This conservation law, which we've just derived, is completely equivalent in this form to the soft photon theorem. Now, we've used rather different language. We've talked about angles that things come in from plus and minus infinity, and it's 3 or 4 pages of algebra to rewrite all of this in terms of the standard plane wave scattering states. And after you dot I's and cross all the T's, you find that it's just exactly the soft photon theorem. Now, the logic can be reversed. You can start with the soft photon theorem, and you can, from the soft photon theorem, if you know where you're going, you can deduce that these operators, Q plus epsilon and Q minus epsilon, obey this relationship, and therefore that abelian gauge theories have an infinite number of conservation laws. Now, we're used to thinking of conservation laws as synonymous with symmetries by Noether's theorem, and this is no exception. What are the symmetries that are associated with this conservation law? Well, all we have to do is to compute the commutators, do some gauge fixing, compute the Dirac brackets, and put an I in. And we only need to compute the commutators up at null infinity, where everything is weakly interacting, so this is an exact computation, we just take that expression, classical expression for the charge, turn everything into an operator, and see what happens when we commute it with the gauge potential. And of particular interest are the tangential components of the components of the gauge potential tangent to the sphere at null infinity, and one finds that they transform by the derivative of this function epsilon. So the symmetries that I'm talking about that give us the conservation laws. Of course, we could have started with the symmetries and worked backwards. In fact, that is how we did it. We started with the symmetries and worked backwards and got the conservation law. But these symmetries are large gauge transformations. We're used to thinking of gauge transformations as trivial, but we can only show that they're trivial if they die off at infinity. These gauge transformations do not die off at infinity. They go to epsilon. But they're really doing something rather peculiar because they go to, if you fix the angle and go to future null infinity, you get a different gauge transformation than if you fix the angle and go to past null infinity. The gauge parameter agrees at antipodal points. In other words, the gauge parameter at the north pole of null infinity agrees with the gauge parameter of the north pole of future null infinity. It takes the same value as the gauge parameter at the south pole of past null infinity. Another way of saying it is that if you have a light ray that crosses Minkowski space, the gauge parameter must go to the same value at either the beginning or the end of the light ray. And these act non-trivial on physical states and can be measured with a variety of different methods. And this will give us the, I won't go into this in detail, but give us the electromagnetic analog of the well-known gravitational memory effect. There's a kind of hysteresis in electromagnetic phenomena which can be described in a variety of different ways. Now, all of this implies that the vacuum in abelian gauge theories is infinitely degenerate. So suppose we have one vacuum state, 0, which is annihilated by the Hamiltonian. Well, if we take this Q plus, suppose we're talking about the vacuum defined near future null infinity. If we take this Q plus and act on it, we get another state which is annihilated by H. And we know, because we know that H, as we just argued, H commutes with this operator. It's conserved. So now we have two states that have 0 energy, but they're definitely different states. In fact, they have different angular momentum because the photon carries spin. So we can think of these different vacua in different ways. We can think of them from the previous transparency. We can think of them as different large gauge field configurations. We just do a gauge transformation and the vacuum classically, they exist even classically, and they can be characterized by the flat connection on the sphere at infinity, arbitrary flat connection on the sphere at infinity, or we can think of them as differing by the addition of soft photons. You take one vacuum and you add a soft photon, you get another vacuum. So abelian gauge theories have infinitely many degenerate vacua. Now, because this operator Q can be written as a surface term at infinity, We can say that the vacuum has soft hair. The vacuum isn't, all vacuum are not the same. It has different kind of zero energy hair. But this hair really lives at the sphere at infinity, because this can be thought of as a boundary term. So the usual way to think about it is, if you take a particle and you lower its energy, its wave function spreads out. And if you're not being careful, you might say, okay, why do I care? I take its energy to zero, it's gone off to infinity. It's not there anymore. But one of the things that we've learned in the last 20 years thinking about quantum field theory and quantum gravity is that the boundaries of space are very important, and we should keep track of what's going on there. And indeed, if we ignore this fact that the vacua are degenerate, we will run into various kinds of contradiction. Now, these large gauge symmetries are spontaneously broken. The generator does not annihilate the vacuum. That's the definition of spontaneous symmetry breaking. And they create a soft photon. And so these soft photons are the Nambu-Goldstone bosons of spontaneously broken large gauge symmetry. Now, there's a completely parallel story for gravity. In fact, the gravity story was worked out first, and after we worked out the gravity story, it's the first example that I know of where gravity was understood before electromagnetism, and it actually is more complicated. Calculations are a lot longer, but there's a Newtonian potential in general relativity, which obeys the same kind of antipodal matching condition. That gives us an infinite number of conserved charges, which are called super-translation charges. And they are, just as the large gauge charges I discussed are generalizations, angle-dependent generalizations of electric charge, the super-translation charges are angle-dependent generalizations of the total ADM mass. And if we don't choose the function parameterizing it to be a constant, the operator acting on the vacuum will create soft gravitons. There's a conservation law, and the Kamp's matrix elements of this conservation law are the soft graviton theorem that Weinberg showed applied to any consistent quantum theory of gravity. And the symmetry is not exactly, but close to what Bondi, Vanderberg, Mester, and Sachs discovered in 1962, the so-called BMS supertranslations. And the associated memory effect in this case, which might hopefully be measured, is the so-called gravitational memory effect. Now, unlike in quantum electrodynamics, which we understand very well, in gravity, we are learning new things. We've discovered some new symmetries by thinking along this line. And moreover, there are precious few pieces of information that we don't know much about what quantum gravity has to look like. And now suddenly we have a lot of information about the symmetries that must be obeyed by any consistent quantum theory of gravity in Minkowski space. Okay, now I'm going to turn. So that's the end of my review of the relationship between soft theorems and conserved charges. Now I'm going to discuss the famous black hole information paradox. So what is the black hole information paradox? So you start and you collapse a bunch of things, textbooks, clocks, graduate students with PhD theses. I understand that in Chicago there's information in these theses. So we could have a lot of information going into making a black hole. We could make it in many ways. And then powerful theorems in general relativity, which I will argue have been misinterpreted, suggest or say that very quickly, on a very short time scale, this will settle down to a black hole characterized only by its mass, charge, and angular momentum, and not carrying any hair, which records any memory of what made it. And then Hawking says that after a long time, if quantum effects are weak, this will start to evaporate, and then after even a much longer time after it starts, it will completely disappear, and there will be nothing left, nothing to record, no record of the information that went in to make this. So there's been a lot of discussion of this, and while I think that there are when this argument first was made, it seemed plausible, and many of the people who listened to it were convinced that, in fact, information was destroyed in the real world by this kind of process. But as the years went by, for a variety of reasons, it became less and less palatable, so that there's now very few people that believe that the information is really destroyed in this way. Nevertheless, there has not been a clear flaw in the argument pointed out, or at least not a flaw that has been universally agreed on. So now I want to say that these new developments, investigations which were not started in order to, we didn't say, what do we need to solve the black hole information paradox? We were thinking about other things, but this points to two flaws, or not two flaws in the arguments, but two flawed assumptions. So the first thing is that the vacuum we've shown is infinitely degenerate. So the vacuum can store an infinite amount of information, and it's perfectly possible that this quantum state of the outgoing Hawking radiation could be correlated with the final vacuum state in such a way that there is overall quantum purity. The other thing is that black holes must carry some kind of hair according to these conservation laws. Because I can take those slices that I was putting through past to future and past null infinity and compute the conserved charges, and I can take the slice, and if I want to complete it, have a complete slice, and there's a black hole in the space-time, I have to pull it through the black hole. And as time goes on and the black hole evaporates, some of those charges will be carried out through the part of the space-time outside the black hole, and in order for the overall charge to be exactly conserved, there must be some mechanism for the black hole itself to also carry those charges. Now, we're familiar with one example of this already, and that is just energy momentum conservation. if we actually do the calculation of Hawking radiation, we get a thermal flux of particles with some probability distribution coming out, and that will not conserve energy. A thermal flux will have an energy spread. So it will not conserve energy exactly. It will only, it will not conserve energy exactly. So by hand, we put in that the black hole must react in such a way so that energy is not conserved just approximately or on the average, but exactly. So by hand, we believe that we should enforce one correlation between the quantum state, the quantum characteristics of the black hole, namely its energy, and the quantum characteristics of the outgoing radiation, namely their energy. So that introduces one correlation, and then you get three more with momentum conservation. We think that the total momentum is conserved. But now that we have infinitely many conserved charges, the ones from electromagnetism and infinitely many more from the soft graviton theorem, there must be an infinity of correlations between the quantum state of the outgoing radiation and the quantum state of the black hole. So the black hole must carry some kind of hair. So both of these assumptions are called into doubt. And the technical point here is that the no-hair theorems imply that all black holes are equivalent up to diffeomorphisms, but of course some diffeomorphisms are non-trivial. And so the fact that they're all equivalent up to diffeomorphisms doesn't mean that they're all physically equivalent. And indeed, one can see explicitly that if you perform a supertranslation on a black hole, you change its angular momentum. Just like when you do a supertranslation on the vacuum, you change its angular momentum. Now, of course, there have been lots of flaws discussed in Hawking's arguments in the past, and I think it's fair to say that there's been ways around most of them discovered, and that could happen here too. But so let me summarize to be clear what we have found so far. There's a flaw in the assumption that clearly needs to be addressed to see what its consequences are. We haven't resolved the information paradox. Resolving the information paradox, to me, would mean understanding exactly how the information gets stored, reproducing the quarter in the Bekenstein-Hawking area entropy law, and calculating the curve that tells you how fast the information gets returned out to infinity. But the nature of the flaw suggests a lot of concrete new avenues of investigation. And in particular, in very recent work, we've analyzed in more detail how it is that the black hole can store information about large gauge or supertranslation charges. All right, so what am I drawing here? I'm drawing now a picture. I'm going to turn on Hawking radiation in the next transparency. Here I'm just considering classical black hole formation. So I have a shell of matter that comes in, collapses, makes an event horizon, there's a singularity, and a black hole. But now my conservation law, which equates conserved charges at the past of the future and the future of the past, doesn't really care about what's going on there. So my conservation law is still completely valid. There's still an infinite number of conserved quantities. But if I want to write them now as integrals over the bulk, I need to take into account, well, in the past it's just the same, but in the future I have to add an extra term, so a natural way to extend the surface would to go up along Scri plus and then down along the event horizon to the point of black hole formation there. And when I analyze that expression, again, I get two terms, one linear in the photon, in the electromagnetic or the gravitational field, and one that involves radiative degrees of freedom. And the linear term has a piece here and a piece here. So we can have zero modes of gravitons or photons here, and we can also have zero modes of gravitons or photons here. That is, if we want to give a complete description of the Hilbert space on this complete Cauchy surface, it requires specifying modes here, and those modes must include soft photons or gravitons on the horizon. But these soft modes have a peculiar characteristic that they can also be thought of as boundary terms, and the one on the horizon can be thought of as a boundary term up here. So this soft graviton can be thought of as a kind of a boundary mode that lives at the future boundary of the horizon. So, by the same argument that gave us an infinite degeneracy of vacua, we also get an infinite degeneracy of black holes with the same mass but different quantum numbers of different soft gravitons, different angular momentums, and so on. Now, the last question I'm going to ask is, could we measure that? Maybe it could happen that somehow you add soft gravitons to a black hole, and then you can't ever discern from anything that happens in the future. Well, there might be different ways of discussing how you measure the soft gravitons. There might be something like the memory effect, but I'm going to describe something a little different. I'm going to talk about what happens now if the black hole evaporates. So let's let the black hole evaporate. So then instead of going up and meeting null infinity up here at some late time, well, it doesn't quite meet null infinity, but in the Penrose diagram it does, I'll let it evaporate. And so what happens is the Hawking photon come out, and then in the far future there's nothing. And now we can take this QF here, and we can write it as a bulk integral either over this Cauchy surface, or we can write it as an integral over this Cauchy surface, and these two things must be exactly equal. And so suppose I know that before I act with QF, or I measure, that the incoming state here goes to some outgoing state. Psi in on the green slice goes to psi out on the blue slice. Now if I take QF and act on psi in, I know from the conservation law that that state must evolve to QF on the out state. Now QF on the out state differs from the out state in a very complicated way. It adds soft gravitons, but it also adds various phases. There's also the hard terms in the charges. Now, in the incoming state here, let me talk about, for simplicity, the large gauge charge. I could make a black hole with neutral objects, and then there would be no hard terms on here, and I would have only soft terms. So I would create a soft graviton on the horizon of the black hole. this operator will create a soft graviton on the horizon of the black hole. So I find that QF, that a black hole with a soft graviton on the horizon, evolves after Hawking evaporation to a different outstate that can be deterministically related to the outstate for the black hole without the soft graviton. So before we had only one piece of information. We thought that just the energy, the angular momentum, and the electric charge, okay, more than one, but some small number of pieces of information. Now we have an infinite number of pieces of information about what comes out here. Now, since there's a finite number of incoming states, you might think of some, well, let me say that in a different way. Okay, so let me just have a concluding comment that black holes carry supertranslation charge, which can be described as soft gravitons or photons. They transform under the supertranslation charge, and they carry soft photons or gravitons. These give us some information about what went into the black hole. They record something about what fell into the black hole, and they record it at this boundary, the future boundary of the horizon. For a variety of reasons, which I could explain, we think it's unlikely that this solves the information problem, or that this mechanism can store all the information about everything that fell into the black hole. However, this is just the beginning of the story, because there are more symmetries, which we don't understand very well. They're very powerful symmetries, and their structure hasn't been studied much. They're mysterious. Those will give us more pixels. There are also implications of the vacuum degeneracy for what we mean by information at null infinity. And so there are a number of things here which give us new ways to think about the information problem. We don't know whether it will give us a complete picture, but there's a lot of concrete calculations we can do at this point to try to understand it better. Thank you.
Thank you.
There's an old paper by John Kane viewing the photon as a number Goldstone boson of the breakdown of the Poincare symmetry. Does yours relate to that?
Yeah.
There's an old paper by Björn Kane viewing the photon as a number Goldstone boson for the breakdown of Poincare.
Yes. I think that for the breakdown of Poincare,
I guess it's translation to get the right quantum.
wait, but I would say Poincare is not spontaneously broken.
Well, BJ says it is. So. He gets a equation.
That might be right. Yeah, that probably is right, because actually in these different vacua, they might not be exactly Poincare invariant. They carry some angular momentum. You might think from that there is a unique Poincare invariant vacuum, but I don't think that's the right way. It's more the differences in soft photons that that is important.
Yeah, so on the black hole information issue, I would have thought that the difficulty is not so much where you find, getting enough degrees of freedom with the black hole, but the fact that, at a time before the black hole is evaporated, you've got an enormous amount of entanglement between, the Hawking radiation or other things outside the black hole and things that, at least in a semi-classical treatment, degrees of freedom that would be inside the black hole, and then, you're either stuck with violating, with semi-classical treatments being wrong, or causality issues of getting the information out, and unless you do it at a final burst, which, has difficulties as well, et cetera. So, I mean,
I think those arguments would have suggested that what I just said happened can't happen. Those arguments would have suggested that these infinite number of conservation laws can't actually exist.
But that's completely consistent. I mean, if the conservation laws are like the ones at null infinity that I'm more familiar with, I mean, those are fine. And that's not violating classical or, I'm sure, semi-classical physics. So that's really what my question is. I mean, are you saying that there is a breakdown in classical or semi-classical general relativity associated with this picture?
My discussion,
or is there some mechanism to break the entanglement or get the entanglement out? Or, well, that's my question.
Okay, so my discussion here assumes that there is some unitary description of the process. So if there isn't a unitary description of the process, then symmetries do not imply conservation laws. There's no reason to think that energy should be conserved. If physics is not ultimately unitary, then I can't make my argument. I'm assuming that it's unitary. The surprising thing is that there is so much that we can learn and see in detail just from conservation laws that can tell us something about the nature of black hole evaporation. In other words, there are apparently an infinite number of correlations between the Hawking radiation and the black hole that we can understand just from an infrared analysis without using string theory or any microphysics. I'm not assuming unitarity. I'm saying that I am assuming unitarity. I'm not proving unitarity, but I'm saying that we have a lot more tools to discuss what this process looks like than we thought.
Let's see. So if instead of having asymptotically flat space, you had ADS4, then we wouldn't have the symmetries, or we do have the symmetries.
Yeah. So one of the things that that you taught us, Juan, is that boundaries of spaces are very important. And spaces with different boundaries have behaviors which really can be qualitatively much more different than we might have expected. And in ADS4, for example, there's a gap. There's no soft photons. And people have tried, most notably Don Merolf, have tried to somehow get BMS or something by starting with ADS, which only has a finite number, ADS4 only has a finite number of asymptotic symmetries, and going to the large radius limit, and it seems to be very hard to do. And now I think that the black hole information paradox takes its sharpest form in Minkowski space. It can be phrased in anti-de Sitter space, but it's not as striking as it is in Minkowski space, and that is the best place to sort of corner the beast. And so anyway, and I'm pursuing the idea that these symmetries can help us understand something about it, but I don't know how to connect that with a long, low curvature limit of anti-de Sitter space.
So it seems like if I form a black hole out of massive stuff, then the instate's coming in from past infinity. And so how in what you're doing do you incorporate the structure of what's coming in from the past infinity rather than null infinity?
Right. So there are 4 papers on that subject, one by myself and my students, and 3 by Campiglia and Latta. And I recommend the one by Campiglia and Latta, who I think did it in a much nicer way than but one knows there had to be a story. There had to be a beautiful story, because when you derive the soft photon theorem, you don't, when a field theorist derives the soft photon theorem, you don't really care whether the particle has a mass or not. On the other hand, in the way I discuss things, it seemed to be very important that the things were coming in from null infinity. And indeed, there's a history in the relativity literature, people like Winokur and other people who have tried to tried to incorporate the analyses of null infinity in the general relativity literature to include massive fields that you can't put data for a massive field at null infinity. You have to put it at past time like infinity, which looks like a very singular thing to do. Now, there was some beautiful work by Ashtekar in the early 80s who was doing an analysis of spatial infinity and used a hyperbolic slice. And this may be the answer to the ADS question. And they resolved the spatial infinity using a hyperbolic slicing and studied the structure of it. And recently, Campiglia and Latta have given a beautiful analysis of time-like infinity by using a hyperbolic slicing involving anti-de Sitter spaces. And using that, they've extended all this to include massive particles. And I encourage you to read their very beautiful papers, and it works out in a nice way. And at the same time, I think one of the places this is going is that the kind of holographic structure of anti-de Sitter space, that Minkowski space secretly holds the holographic structure of anti-de Sitter space, not by being the large radius limit of ADS4, but by being very nicely represented by this hyperbolic slicing.
Okay, I think, oh, yes, one more.
Sorry, this is about the counting. So you sort of motivated why there should be sort of infinitely many soft gravitons out at infinity. It's graph.
Yeah, yeah.
But now at the horizon, there would be presumably finitely many by sort of scaling by the horizon area. But why do you say that you're nowhere near enough? I mean, how did the counting go there?
Well, there's enough in the sense that there's enough modes lying around there. And in fact, in a way, there's too many. And but in order to excite if you have a black hole and you want to excite a soft graviton or a soft photon, you need to throw something into the black hole. And soft particles are the same as the memory effect. So you throw something into the black hole, and it's still a black hole afterwards, but it's been the way that the null generators are tied together has been shifted in a subtle way. Now, these shifts can take place formally over arbitrarily small scales, so you could have very small soft gravitons. They still have an infinite temporal extent. They're zero frequency, but they're localized. But you couldn't excite one of those unless you could throw something in smaller than the Planck length, and there is nothing smaller than the Planck length. But I don't think, so there's a lot of them, but I don't think that the way that they couple to what goes in can diagnose, can record everything. It can record some things, but it can't record it. It can't record I don't think it can record everything. I don't have a proof of that, but I don't think it's true.